Hello, my name is Jared, and this is my homework 2 for my Transport 2 class. So the problem we have here is that we have a capillary that is filled on equal volumes of water and deuterated water on the left and right hand sides. This capillary tube is 10 centimeters long, and from 0 to 5 centimeters we have pure water, and from 5 centimeters to 10 centimeters we have deuterated water, which is heavy water. It has higher density and a higher molecular weight than regular water. And we know it's given in the problem that the capillary has a constant cross-sectional area, meaning that the volume of water on the left-hand side is equal to the volume of deuterated water on the right-hand side. We're also given the density of water and deuterated water, and also the molecular weights. And I'm using a superscript here to represent density, because we know that pure component mass concentration or density, that's different than the mass concentration in a mixture. And I just like this notation because it lets me differentiate between what am I talking about, mass concentration or pure component density. And we're told that at T equals 0.1 seconds, the maximum molar diffusive flux is equal to 2.78 moles per square meter per second. And well, for this problem, it's a unsteady state diffusion problem, because the concentration of the components at any point in the mixture, it's going to change in time. So we have functions not only of position but also of time. So I just use this here, is that the z component, we don't know where it's at yet, but then we know that time is 0.1 seconds, and we know that that's the maximum molar diffusive flux, and that's 2.78. And so the first problem is we need to find the overall mass flux, which is denoted with this little n, that corresponds to the maximum molar diffusion flux, meaning that mass flux is also a function of position and time. So the overall mass flux corresponding to the maximum molar diffusion flux will occur at the same location at the same time. And so we're going to start off this by with some assumptions. This first assumption goes without saying. We are ignoring hydrogen exchange. So when you mix deuterated water with regular water, there will be an interchange of protons, deuterium atoms, and hydrogen atoms to form HDO. We are not going to be considering that at all. That would make the problem extremely complex, and we're not going to be dealing with that. Second assumption is that no volume change due to mixing, meaning when you because when you mix liquids together, volume 1 plus volume 2, when you the mixture isn't always the sum of the individual components' volumes before mixing. But what we're going to say here is that there is no of that effect coming on, so that the total volume is the volume of water on the left plus volume of deuterated water on the right, which these two volumes are equal. So it'd be 2 times the volume on either side. And the third assumption is that the total molar flux is negligible and can be ignored. And this assumption just comes to, we're going to talk about why we can say that it's negligible and approximately 0. It's not actually equal to 0, as we'll see, but this assumption is needed because I tried solving this problem without the assumption that the total molar flux is not equal to 0. And I could not solve it. So in order to solve this question, I need this assumption. So let's talk about why we can assume that the total molar flux is equal to 0. And so in this analysis here, this is what I'm doing. I'm going to take the capillary tube at t equals 0, where there's equal volumes of water on the left-hand side and equal volume of deuterated water on the right-hand side. They're both pure components. There's a barrier in between. We're now going to let it go to t equals infinity when the whole system will be at steady state, and the concentration of the components, there's no more concentration gradients. And at that moment, we're going to then just put the barrier back in. And so in this analysis, we're going to see the total molar concentration on the left-hand side and the total molar concentration on the right-hand side. What is that at t equals 0? And then we're going to see what the total molar concentration on the left-hand side and total molar concentration on the right-hand side are at t equals infinity. And then we're going to analyze how the total number of moles on either side changes with time. So let's take the total molar concentration on the left-hand side. We know that the total molar concentration is just equal to the molar concentrations of the individual components, but since there's only pure regular water on this left-hand side, that's just equal to the total molar concentration is just equal to the molar concentration of water on the left-hand side, which is, we know that the molar concentration can be expressed as the mass concentration of water divided by the molecular weight of water. And what's the mass concentration of water on the left-hand side? Well, since it's pure water, the mass concentration is just denoted, is just the density of water. The superscripts, remember that the superscript represents density in my mind, at least. So it's the total molar concentration on the left-hand side is equal to the density of water divided by the molecular weight of water. We plug in those values, and we'll see that the total molar concentration on the left-hand side is 55.56 kilimoles per cubic meters, or 55.56 moles per milliliter, or liter, yeah. And then, so 55.56 kilimoles per cubic meter. And then on the right-hand side, we're going to do the same thing. So on the right-hand side, the total molar concentration is the sum of the individual components' molar concentrations. And since it's only deuterated water on the right-hand side, it's just the total molar concentration is just the molar concentration of deuterated water on the right-hand side, which is equal to the mass concentration of deuterated water on the right-hand side divided by the molecular weight of deuterated water, which the mass concentration is just equal to the density again. And we'll see that the total molar concentration on the right-hand side is 55.5 kilimoles per cubic meter. And what do we see here? That the total molar concentration on the left-hand side and the total molar concentration on the right-hand side, they are really, really similar. And so let's turn our attention to what happens at t infinity. So we let the whole system go to steady state, equilibrium, where there's no more concentration gradients. And then we're going to put the barrier back in, and then we're going to see what the total molar concentration is on each side. And since this is the volume on the left and the volume on the right, they're both the same. And since it's at equilibrium, we know that the total molar concentration on the left-hand side is equal to the total molar concentration on the right-hand side. So we'll just denote it as left/right, they're equal. So what is the total molar concentration? Well, that's equal to the total number of moles in the system divided by the total volume. So that's moles of water plus moles of heavy water divided by total volume this is where our assumption that the total volume is the sum of the individual volumes. That's equal to 2V. So how many moles of water do we have? Well, we take the density of water and then we multiply by volume, and that will give us the mass of water on the left-hand side at the beginning. And after t infinity, that mass is equally distributed through the entire thing. So if we then divide by the molecular weight of water, we'll get the moles of water. And then we do the same thing. It's just the density of heavy water times volume divided by molecular weight of heavy water. that's the moles of heavy water. And then we divide by 2V, we factor out the V, and the V's cancel, and then we get that the total molar concentration on either side is equal to 1/2 times the density of water divided by molecular weight of water plus 1/2 times the density of heavy water divided by molecular weight of heavy water. And so we see that the total molar concentration on the left-hand side and the total molar concentration on the right-hand side, they're equal, and they're equal to 55.53 kilomoles per cubic meter. And what do we see here? That the total molar concentration on the left-hand side is approximately equal to the total molar concentration on the right-hand side, which is approximately equal to the total molar concentration at equilibrium. So we could say that the total molar concentration on the left-hand side at t equals 0 is approximately equal to the total molar concentration at equilibrium, and the total molar concentration on the right-hand side is approximately equal to the total molar concentration on the right-hand side at equilibrium. And so we could see that, you know, the molar concentration isn't really changing on either side. So let's just analyze exactly like the actual number of moles that change on the left-hand side. So if we take the total molar concentration on the left-hand side at t equals 0 and multiply it by the volume, that will give us the total number of moles on the left-hand side. Similarly, the same thing for at equilibrium. We take the total molar concentration at equilibrium times volume. And so if we analyze what the net change in total number of moles on the left-hand side is, we'll get this expression here because they both have V, it factors out. So we'll get V times the difference between the molar concentration at equilibrium minus the total molar concentration at t equals 0. And that is just negative 0.03 times the volume. And so the total number of moles on the left, it's how it changes, it's negatives, meaning that the total number of moles on the left-hand side is decreasing. So the total molar flux is not equal to 0, but it's pretty close. And you know, if the volume is really, really, really big, then the total number of moles that leave the left-hand side will be really, really great. So as long as this is sufficiently small enough, we can ignore the net change in moles on the left-hand side. So what is the volume? Since this has constant cross-sectional area, that's just a definition of a cylinder. A cylinder is any object that has constant cross-sectional area. So it's equal to the cross-sectional area A. So the volume here is equal to just the cross-sectional area multiplied by how far it protrudes. This is the volume on one side. So it's how far it protrudes is just 5 centimeters, which is 0.05 meters. And then we get this, that the total net change in moles on the left-hand side is negative 0.0015 times A, K, kilomoles. And so as long as the cross-sectional area is sufficiently small, we can say that the total net change in moles on the left-hand side is approximately equal to 0. So let's just think of something. Say that the area is much bigger than how far it protrudes. Say that the area is 1,000 square meters. If the area is 1,000 square meters, then the net change in moles on the left-hand side would be negative 1.5 kilomoles. And that's a very large area. And that's not a large amount of net change in the moles, even with a large area. But we got to remember that this is a capillary, and the cross-sectional area of a capillary is really, really small. If you were to look up the definition of a capillary, it's, I think the definition is just a tube with hair-thin area, diameter. So we can say that the area of the capillary is much less than 1 square meter, meaning that the total net change in moles on the left-hand side, we could just approximate that to be 0. And since there is no net change in total number of moles on the left-hand side, we could just say that the total molar flux is approximately equal to 0. And that assumption greatly simplifies the problem. So with that discussion out of the way, we can use the approximation that the total molar flux is equal to 0, and we can now solve what the overall mass flux is. So what is the molar flux of an individual component? It's the molar diffusion flux of that individual component plus the bulk contribution term, which would be the mole fraction of the component multiplied by the total molar flux. But since the total molar flux we're approximating to be 0, we can just say that the bulk contribution term is approximately equal to 0, and so that the molar flux of the individual components is approximately equal to the molar diffusion flux of the individual component. And now, so we have J max, which is the maximum molar diffusion flux, equals 2.78. Well, it corresponds to water. Why does it correspond to water? Well, if we take this direction here to be positive, then water goes in that direction. And flux is a vector quantity. So 2.78 means it's going to the right. And which component do we know that's going to the right if we look at the way we drew our original picture? Well, water, regular water, is going to the right. So that must correspond to regular water. And now where does the maximum molar diffusion flux occur? Well, that occurs at the maximum magnitude of the gradient of the molar concentration of that component. I'm just doing magnitude because the gradients can be negative and stuff, so I just magnitude, so it's just positive, so the maximum of that. And where is the maximum magnitude of the concentration gradient? Where is that? Well, that's at the center line, because at t equals 0.1, there's going to be a large change in molar concentration of water on the left-hand side and right-hand side. So that's where the maximum gradient of the molar concentration of water is, at 5 centimeters. And since we know that the sum of the individual components of the individual components' molar diffusion fluxes is equal to 0, and this is a binary mixture, then we know that the molar diffusion flux of deuterated water at 5 centimeters, it has to be at the same location though, because these are functions of position and time. So the molar diffusion flux of deuterated water at the same position and same time as the molar diffusion flux of regular water is just equal to negative the molar diffusion flux of water. So it's negative 2.78. And since we know this relation, that the total molar flux of a component multiplied by the molecular weight, so moles per square meter per second divided by moles, and then you get mass up here, so that's mass over square meter per second. That's just the mass flux of the component. Using this relationship, we can get that and this is, we'll start with an exact answer for the total mass flux. So the total mass flux at 5 centimeters and t equals 0.1 seconds is equal to the molar flux of water at the same location and same time multiplied by the molecular weight of water plus the molar flux of deuterated water at the same position and same time multiplied by the molecular weight of deuterated water. This is an exact relation, but since we are approximating the molar flux of the individual components to be equal to the molar diffusive flux of the individual components, we can approximate the total mass flux to be equal to the molar diffusive flux of water at 5 centimeters and 0.1 seconds times the molecular weight of water plus the molar diffusive flux of deuterated water at the same location and same time multiplied by the molecular weight of deuterated water. And when we put all that together, we get that the overall mass flux corresponding to the maximum molar diffusion flux, meaning it at the same position and same time, is equal to negative 5.56 kilograms per square meter per second. All right, now on to the second part of the question, which says, make an order of magnitude estimate for the maximum driving force for diffusion at t equals 0.1 seconds. So we're going to start off, since these are liquids, well, fixed diffusivity for liquids is approximately equal to 10 to the negative 9th power meters squared per second. And if we just look at Fick's law, which says that the molar diffusive flux of component 1 is equal to negative the gradient of the mole fraction of the component 1 at that location multiplied by the total molar concentration at that location times the fixed diffusivity. And this gradient here is just the driving force. And so we know the molar diffusive flux, we know we're approximating the fixed diffusivity to be this, and then we just solve this for D1, and then we'll just have to calculate what the total molar concentration is. So where does the maximum driving force occur? Well, that occurs at the same location as the maximum molar diffusion flux. And because this is kind of just the opposite of what we said before, is that the maximum molar diffusion flux occurs at the location of the maximum gradient. So it's just we're flipping that saying around. So that occurs at 5 centimeters. So we have this relation here, that the maximum driving force is equal to negative the maximum molar diffusion flux divided by fixed diffusivity, which we're estimating, and the total molar concentration. And well, what is the total molar concentration? It's not equal to, well, it's approximately equal to the molar concentration at equilibrium. So because the total molar concentration is a function of time and position, right? So it has to be the total molar concentration at 5 centimeters plus 0.1 plus, not plus, sorry, and time equals 0.1 seconds. So let's go back to our discussion on molar concentrations. So molar concentration on the left-hand side initially, and the total molar concentration on the right-hand side at initially, and the total molar concentration at equilibrium. These are all approximately the same, and since we're doing an order of magnitude estimate, we could use either one of these, but I'm just going to use the average of these two total molar concentrations. And so I say that the total molar concentration at 5 centimeters and 0.1 seconds is just approximately equal to the total molar concentration on the left-hand side initially plus the molar concentration on the right-hand side initially divided by 2. So just the average over the two, and you'll get the total molar concentration to be 55.55 kilomoles per cubic meter. And we plug this in, and then we get that an estimate for the maximum driving force, which we get 50,000 1/meter. Now we can move on to the third part, the graphs. Before I talk about the graphs, though, I'll explain something really fast. So with my graphs, I can ignore this stuff up here. It's just a random piece of paper. With my graphs, I talk about areas under the curves. So if you take the mass concentration of a component and integrate that over the entire volume of the component, that's equal to the mass of component I in the entire system. But dV, since it's cross-sectional area, this was V1 to V2. We'll actually ignore that. Cross-sectional area, mass concentration, dz. We could just make dV, that's equal to the cross-sectional area times how much it protrudes, but the area is constant in the z direction. You pull that out, and so since it's a closed system and there's no mass entering, the total mass of component I must be equal to a constant, meaning in time, when these graphs change in time, the total area under the curve must be constant, so that mass concentration, the integral of that from z equals 0 to z equals 10 centimeters, that's equal to a constant. So I'm going to be talking about areas under the curve here quite a bit, so I just wanted to have that quick discussion on that so you know what I'm talking about. So let's look at the mass concentration of the individual components at t equals 0.1 seconds. Well, over here you just have pure water, and over here you have no water. Same thing here, you have pure deuterated water and then no deuterated water over here. But then right at the interface, because you've let a little bit amount of time go by, there will be some deuterated water that moves over to this side and some regular water that moves over to the right hand side. And so this green area here is the total amount of, I shouldn't say that because it would be the area there multiplied by the cross-sectional area, the capillary. It's representative of the total mass of water that moves to the right hand side is this green area. And then this red area is the represents the amount of the mass of deuterated water that moves to the left hand side. And we know that the mass flux is negative. There's more mass going to this left hand side, because for 1 mole of, we approximated the total molar flux to be equal to 0. So for 1 mole of heavy water, that goes to the left, and 1 mole of water goes to the right. But deuterated water is heavier, so carries more mass. So the total amount of mass that goes to the left-hand side is not equal to the total amount of mass that goes to the right-hand side. And as you see here, looking at the concentration gradients, these are the slopes. The greatest slope occurs right there at z equals 5 centimeters. And then over here, we've let time pass by more, and this red area is the total amount, represents the mass of deuterated water that moves to the left, and this green area represents the amount, the mass of water that's moved to the right-hand side. And we see that because, same thing as before, that the total mass of deuterated water that moves to the left-hand side is greater than the total mass of water that moves to the right-hand side. So this area here is greater than this area here. And then and then at t equals infinity, there it is at equilibrium, and there is no more concentration gradients. So the concentration, mass concentration, the individual components are just equal to the mass concentrations at equilibrium. Whereas before up here, these were the mass concentrations. These were just the densities of the two components. And then same thing for molar concentrations of the individual components. We have pure H2O, and then no H2O, and then there's pure D2O and no D2O, and then there's a sharp decrease in concentrations of the components right there, and that's where the maximum gradient, magnitude of gradient is right there. And then as time goes on, it will look something like this. And actually, under our assumption that the total molar flux is equal to 0, these curves are symmetric. There's symmetry right along here. Kind of that is symmetric to that, even though, yes, I know that this is all D2O. It's symmetry. And why is that? Well, if we let's see. So this right here, let's use some colors. The fact that the total molar flux is equal to 0 gives us symmetry and makes this kind of pretty. So the total moles of D2O that move to the left-hand side is this. And since that's the total number of moles, represents the total number of moles that move of heavy water that goes to the left, and the total molar flux is equal to 0, then that area right there must be equal to this area here, because this area here represents the number of moles of water that goes to the right-hand side. And we know that the number of moles of water that goes to the right-hand side is approximately equal to the number of moles of deuterated water that goes to the left-hand side. And if we take this up here and kind of just extend that, well, then this area up here is equal to this area down here, because this area up here represents the number of moles of deuterated water that leaves the right-hand side, which equals the number of moles of deuterated water that goes to the left-hand side, which equals the total number of moles of water that goes to the right-hand side, which equals the total number of moles of water that leaves the left-hand side. And then this goes on to T equals infinity until there is no more concentration gradients. So you just have one single line here, although the molar concentrations of the individual components, they're different by a little bit, but you can't really show that, so I just show it as one single line here. And then we'll talk about the molar diffusion flux of the individual components. So there's no concentration. I guess I'll look at this one. So the molar diffusion flux of the component is proportional to the gradient of the molar concentration curve. So when the gradient here is equal to 0, there's 0 molar diffusion flux, and then same here, there's 0, because for both of these, all of these gradients here are 0, except right here in the middle. And then the molar diffusion flux of water, there's a sharp increase to the maximum at z equals 5 centimeters to there, and it's positive because the water goes from left to right, and that's what we designate as positive direction. And then the molar diffusion flux of deuterated water is symmetric of this about the J equals 0 axis, because the sum of the two components must be equal to 0. So you have symmetry along J equals 0 axis for all of these. And we'll skip this one for a second and just look at this. Here, it's at equilibrium, so there's no more concentration gradients, so it's just 0 everywhere. And then here we have the molar diffusion flux of each of the components decreases in magnitude, but then has more amount of the components from 0 to 10 centimeters are able to diffuse, so it's wider here. And then at the endpoints, this has to do with boundary conditions. Since at z equals 0 and z equals 10 centimeters, the ends of the capillary, since water cannot go through it, nor deuterated water can go through it, then we know that the molar flux of the individual components there are equal to 0, because it can't penetrate through that. It's a no flux boundary condition. And since the total molar flux of the component must be 0 at the endpoints, then the molar diffusion flux is equal to negative the total molar concentration, which is not equal to 0, and the concentration gradient, and then the fixed diffusivity. The fixed diffusivity is not equal to 0, so therefore the concentration gradients must be equal to 0. And well, the total, since the molar flux of the component at the endpoints must be 0, and that's approximately equal to the molar diffusive flux of that component, then the molar diffusive flux of each of the components must be equal to 0 at the endpoints, at the boundary conditions of this. And what I was getting at before is that since the molar diffusion flux must be 0, then the concentration gradients at the endpoints, at the boundary conditions, must be equal to 0, meaning this has to do with how I drew these up here, meaning that the concentration gradients of the components at the endpoints must be 0. So the slope at the endpoints of the curves must always be 0 due to this boundary condition. So now we just go and talk about the last point, which is the mass flux. So the total mass flux, initially, it's just going to be pure water over here, pure D2 over here, and then right at the z equals 5 centimeters, there will be diffusion occurring. And since 1 mole of water goes to the right, 1 mole of deuterated water goes to the left, and deuterated water has more mass, then the mass flux is negative. So it goes down to the maximum, or I guess you would call it minimum mass flux. And then as at equilibrium, there's no more concentration gradients, so the mass flux is just equal to 0. And then at the intermediate value, t equals 60 seconds, there's just a net mass flux throughout the entire capillary tube. And it's, since the concentration gradients aren't as sharp at t equals 60 seconds, the mass flux will not have great of a magnitude as before. And it's kind of just spread out over the entire capillary. And with that, I am done, and thank you for watching.